Hi, I'm Lane from Cisco. In this video, I want to talk about cooling innovation in the Cisco 8000 series routers and how we're designing and implementing new ideas for sustainability. So the topics we're going to cover are cooling requirements of different components, what are the parts of the cooling system in an air-cooled chassis, fan power laws and the relationship between how fast the fans are running and how much power they need, traditional versus new approaches to cooling, and then QSFP-DD optic design, or design for cooling with those optics. So the first thing I want to kind of talk about is the fact that we really take a systems approach at Cisco, and especially with the 8000 series. We're not trying to have the perfect optic or the perfect ASIC or the perfect fan from a power perspective. We're really looking at how they all work together. If you ran your fans at 100%, then your ASICs would take less power, but the fans would take a lot of power. So you really have to balance it all out. And each of these devices in the system has a different requirement that needs to be met. So for example, for the most part, the optics need to be kept under 75C. We have designed some of the highest power optics to be able to run a little bit hotter, but that's kind of the ballpark range. The ASICs need to go under 110. They do have the ability short term to go up to about 125C. So these ASICs are very hot these days, 2, 3, 400 plus watts, and so they're very challenging to cool. They may often have heat sinks that are very large. The HBMs, or high bandwidth memories, need to be kept at about 90C. This could be a challenge because they're very close to those very hot logic dies in the ASIC. And then each of the other components has different temperatures, and so we're going to be kind of keeping an eye on all of them in order to set how we run the fans. So all of these devices here are thermally sensitive. And one of the challenges that we have to think about in these designs is air preheating. If the air comes in at, let's say, 25C and it hits the optics, well, by the time it gets to the ASIC, it's not 25C anymore. Now that air might be 30C. And let's say I have another ASIC back on a switched fabric card, it's going to be even hotter. So we have to think about how we lay out the chassis in a way that works with preheating. And because the optics are thermally sensitive, we really get them the coldest air in all the chassis designs these days. So what are the components of the cooling system? I think heat sinks and fans are probably the ones that people think about the most. The job of a heat sink is to create more contact area between the hot metal and the air. And so the heat sink will be on top of the optics cage or on top of the CPU or on top of the ASIC. It is taking the heat either directly on the bottom of the heat sink, or example here, not from our product, is with heat pipes, and it's putting all this metal in contact with the air. The heat spreads through the metal, and then the air takes the heat from the metal as the fans drive it through. So lots of different ways you can do heat sinks, and we have heat sinks in lots of different components. One that's often overlooked is thermal paste, and we're not going to get into that a lot of detail, but getting the heat from the hot component into the heat sink is a challenge as well, right? They have to have a good bonding there, so that's where the thermal paste comes into play. Air channels are often also important. How much room do we have to put the heat sinks? How much pressure do we cause to build up? And so a lot of what we have to do is, in our larger chassis, is optimize, for example, the size of the line card so that we can fit the right number of line cards in the chassis, but also have enough air for them to breathe, for lack of a better word. Another important place we've done a lot of innovation is software control. If you took a system in the past, what people would do is they'd say, okay, if it's 25C, we'll run the fan this fast, and if it's 32C, we'll run the fan this fast, and if it's maybe 40C, we'll run the fan this fast. So something like that with a relatively simple stair-step function that only focused on the outside air temperature. This was nice, this is simple, this is one size fits all, but it's not power efficient, and so this is why we're doing some things differently now. One of the key evolutions of the chassis in the last 6 or 7 years is moving to this orthogonal design. If you looked at a traditional service provider chassis like the ASR 9000, what you would see is usually the air comes in just the bottom of the front. We then have a number of line cards, and then the air goes out the back. Okay. The challenge with this design is that The optics down here are getting a different temperature air than the optics up here because the air is getting preheated as it goes up. Back when the optics were a few watts, that wasn't a big deal, or back when we had one optic per line card, it wasn't a big deal. Now that we could have 36 25-watt optics on a single line card, this approach doesn't work anymore. And so now what we have is these called orthogonal chassis designs. And so this is the 8800 series. This is showing, the picture showing an empty cage. If we start to populate it with line cards, what you'll see is that we have, of course, all the optics on the front, but now the air is going straight into those optics. So they're all getting cold air. Behind these line cards, so here's the line cards. Behind the line cards, we have switch fabric cards, and this orthogonal in the chassis, the type of chassis name is the fact that they connect perpendicular to each other, so every fabric card is connecting to every line card. And then behind that, as you can see on this picture on the right, is the fans. And one benefit we have in having this new design is that the entire rear of the chassis is covered by fans, so we don't have power supplies fighting for space there. Okay? So this is the orthogonal chassis design that we use on the 5500 as well as the 8000 series. So now I'm going to introduce some fan terms and talk about fan power. The first term to talk about is PWM, or pulse width modulation. This is how fast we're asking the fan to run. So if the fan could run up to 10,000 RPM, if we we program it with a PWM of 50, it's going to run close to 5,000 RPM. Now, it is an analog device, so it's not going to run exactly that fast. So the RPM will be, plus or minus from what the requested speed is via the PWM. If a fan runs, too far off the requested speed, it'll get marked as failed, and then the fan tray will have to get removed. CFM, or cubic feet per minute, is the amount of air that's actually moving through the system, and so that's a function, of the fan speed and the number of fans. Finally, delta T, or also T-rise, is the increase in air temperature. When we're cooling the system, we have the ability to have some trade-offs between having more air moving through and less T-rise, or less air moving through and a greater T-rise. In general, the latter is better because it's using less fan power, but the same amount of heat is coming out in either situation. Now on the right side, what I want to show you is this fan affinity loss picture. And this is going to illustrate why it's important to keep the fan speeds from going too high under normal operation. So here in the blue, this is the CFM. This is the cubic feet per minute, which tracks to the PWM and the RPM. So this is how fast the fan is going. This yellow line is the power. And you'll see here that it's an exponential power. It is roughly cubic. And it doesn't look exponential over here, but once we get into the right side of the graph, we see that it is exponential and the power is going up dramatically. Remember what I said in the past, a lot of times we would just say, maybe we'll run it at 60, 80, or 100%, and that problem there is in normal operation, you can start getting up into that higher fan power. So what we want to do is we want to run the fan as low as possible, and we especially want to stay under the 50-60% operation for normal use. So how do we do that with the 8000 series in iOS XR? The first step is that we want to look at the hardware that's in the system. So we're going to set a starting fan speed based on the inlet sensor, so how hot is your central office or data center or co-location. Second, we look at the different cards installed. Do I have a 100 gig card that might require lower requirements? Do I have a 400 gig card, an 800 gig card that have more requirements? We next look at the optics. So do I have DAC cables? Do I have gray optics like DR4s and FR4s? Do I have ZRs? Do I have a ZR Plus? We'll often also look at actually if the ZR is in the top or the bottom of a cage, because we can optimize it if it's in the top of a cage. Okay? So based on that, we're going to have a starting speed. So let's just say, for example, I have, this is 22, 23, blah, 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 up to, let's say, 40C, and then I have, gray optics, ZR optics, ZR Plus. There's going to be a number in all of these, which is our starting fan speed. So that's where we get started. The second part is this dynamic fan adjustment. So what we're going to do to keep the fan as low as possible while keeping everyone happy is that all the devices in the system which are thermally sensitive, they can vote on the fan speed they need. So let's say the ASIC says, hey, I'd like the fan to run at 32. But one of the optics said, I need the fan to run at 35. We're going to run the fan at a 35 PWM to keep everybody happy. So by this way, we're actually taking real-time feedback in order to determine the fan speed versus a one-size-fits-all approach. And in this example here, I'm showing you the fan power for our one rack unit 32 by 400. This is the temperature here, and this is actually power in watts here. So this is incredibly low power for this much bandwidth. We treat the gray optics and the copper cables the same. So there's, if those are what's in the system, it usually ends up being something else, namely the ASIC that is driving the requirements. But if we get into, for example, ZR plus optics, ZR plus optics, they may be the ones that are controlling the fan speed. So what we see here is if we have these gray optics or copper cables, we're going to be at this relatively low fan profile. If we're running with ZR optics, we may be in this range for normal operation. Occasionally, if you have higher temperature issues, we're going to have to increase the fan power. Still not that much, given that this is a 12 terabit system, but most of the time we stay in this range of between maybe 5 and 30 or 40 watts of fan power, which is just absolutely excellent compared to the kilowatts we used to have to run for these type of systems. Okay. So one of the important things we have to do is cool optics, and in the 400 and 800 gig generation there are two main choices, QSFP-D and OSFP. And the two most important differentiators are that QSFP-DD is backward compatible with older generations of QSFP, whereas OSFP is not. Second, QSFP-DD has a cage-mounted heatsink, whereas OSFP has an integrated heatsink. There are pros and cons of both, but the reason we really like QSFP-DD is that cage-mounted heatsink allows for continuous innovation. Back when we first designed the 8000 series, we were thinking about 8 to 12 watt optics. Well, that now is 25 watt optics, and so we've had to do a lot of innovation in cage design, thermal paste design, heatsink design, board design, etc. And so having the cage be one piece and then the heatsink, and actually I don't know if thermal paste is on the heatsink, but it's mostly clamps. But the heatsink design innovation is really beneficial versus sort of locking down a heatsink in OSFP. So there are lots of ways that you can put these optics cages or these optics into boards. You may hear terms like belly to belly or stacked or whatever. These are just commodity cages that we and others buy from certain vendors. You can mix and match what you need for a particular environment. So for one of our systems, a belly-to-belly cage may be good. For the other, a stack cage may be good. For one, certain heatsink may be the right way. Maybe if the air is flowing in a different direction, like the SR 9000, we want to have a different heatsink. At the end of the day, the goal is to cool the optics. It's not to have the best heatsink or the best cage or whatever. And where we've ended up on the 8000 series is that for all of these devices, we can cool ZR Plus on all the ports. Now, it may be that if you have a ZR Plus on the bottom row of a device, we may run the fan a little bit faster, but we can still run them with good fan power in all configurations. So, despite the fact that QSFP-DD was designed originally for 12 watt optics, we've now got it running 25 plus watt optics, and in the 800 gig generation, we're designing around 30 watts. Okay. So it was kind of a whirlwind tour of cooling on the 8000 series. The key innovations are that we've evolved chassis designs to be very efficient. We do some innovation in fan control, so we don't run the fans any faster than we need to, and we do a good job of integrating with these QSFP-DD optics so that we can cool lots of long-reach optics while still maintaining a good fan speed, which means that we have good sustainability with lower system power. Okay, thank you for your time. Please feel free to leave a comment, and I encourage you to explore the other videos in this series.